Okay, everyone, thanks for coming. Welcome to our 1 o'clock press conference. This is Changes in East Antarctic Glaciers. And so our speakers today are Kathryn Walker from NASA Goddard Space Flight Center and Alex Gardner from NASA Jet Propulsion Laboratory. All right, turn it over to you guys.
I did something wrong. Hang on. Here it goes. Who's controlling that? Somebody's doing something. Oh, okay. It's magic. Okay. So I'm Kathryn Walker. I'm going to be talking first about the changes that we actually saw in some East Antarctic glaciers. I'll show those in a moment. And then I'm going to pass it to Alex, and he's going to actually talk about the data sets that we've used to see these changes and how they were developed. So these two maps, I'll start with these. On the left side, what you see on the Antarctic continent here is a map of velocities, so surface flow of the ice on the continent. On the right, the Antarctic continent has a map of elevation change. So red is losing elevation, and blue, which is mostly in East Antarctica, is gaining elevation. And the flow fields here around in the ocean just show you basically the Antarctic Circumpolar current. So it goes this way around Antarctica. And those come from the ECHO project, which is also hosted at JPL. So just to cover what we are going to be talking about today, East Antarctica, mostly from the limitations of data that we've had thus far, has long been considered to be much more stable than West Antarctica, which is more dynamic. You can see a lot more elevation change, and if I had a change map here, you would see that they flow a lot faster as well in West Antarctica. So for most of the larger stories that come out of research on Antarctica, we're talking about the western part. But today we'll be talking about East Antarctica, which is generally smaller signals, but still very important. So what we found, just to get to the point, is that using these new flow velocity maps and elevation change maps that Alex will talk about in a moment, we were able to see that glaciers near Totten Glacier, which I'll show in a moment, are changing and have increased their ice loss since 2008, so over the last decade or so, which will show trace back to changes in the ocean in this region. So I'll start out actually on the right. This is a zoom in of the region that we're talking about. So Totten Glacier is this big one here. This little region map shows where we are in Antarctica. Totten Glacier has received some research attention recently and has been more popularly covered because it's the fastest moving glacier in East Antarctica and has been shown to respond to ocean changes as well. But what we're looking at are these 4 glaciers up here in Vincennes Bay, which are a lot smaller than Totten and mostly up till now have looked pretty stable. On the left here is basically what motivated our study, so before Alex and his colleagues developed these sort of interannual velocity maps of Antarctica, all we had was a single snapshot from about 2008 that was published by Eric Renaud and colleagues in 2011. So we just had a stationary view of what velocities looked like on the Antarctic ice sheet. Once Alex and his colleagues developed these later maps using Landsat, we were able to difference those velocities and see how much things have changed since 2008. And so you can see most of the change, again, happens on the West Antarctic section, but then we looked in this little region here and suggested that there were changes that we didn't know were happening. So zooming in on that region, this is a sample elevation change map just from December 2017. And what you can see is we looked at our bay that we've been looking at and compared it against glacier basins across East Antarctica. And what these colors show in these circles is just how much their rates of loss have increased since 2008. So they've each been losing mass over the last decade or so, but Vincennes Bay in particular has been losing elevation at about 5 times the rate it was losing in 2008. And the other one's also Denman Glacier up here near Shackleton Ice Shelf has been losing the slowest, but it still is losing mass. So the reason we care about East Antarctic glaciers so much, and if we see them changing, is that this is where each of those ones that we just showed are. And they're grounded basically below sea level. So as you go back, they are holding back the ice that's in the Aurora and Wilkes subglacial basins, which are two of the biggest subglacial basins in Antarctica. And together, they hold about 28 meters water level equivalent. So if they were to both completely drain, you'd get about 28 meters of sea level rise, which is about 4 Greenlands. So that's why we care about these glaciers starting to move. Just to give a little background on ocean interactions with the ice in East Antarctica, this is the map that we usually look at to describe why West Antarctica responds to the ocean a little more than East Antarctica. There's a lot, down to the seafloor depths in West Antarctica, you get warm water. East Antarctica is generally sort of insulated from that warm offshore water by this cool layer, as you can see the blue. But this is a map that we just created this year, which shows the 2017 seafloor temperatures off of East Antarctica. And what you can see is the white sort of things that are infringing on the coastline are ocean temperatures at about 0 degrees, which is capable of melting ice. So tracing that back, just looking at Vincennes Bay, we used ECHO 2 simulations for ocean temperatures, augmented by sensor-tagged marine mammals, so seals with little CTDs on their heads that swim around and measure temperatures, and some Argo floats, and we could measure the ocean heat content in that bay, which ocean heat content is basically the energy available to melt ice in the ocean. So what you can see is since 1992, there's been this increasing trend in that heat energy, or melt energy in the ocean, and particularly since 2008, it's been increasing at a quicker clip. So these are, just to sum up, so our early results using this new data sets that Alex is going to talk about in just a sec, that we can see these sort of small changes in East Antarctica that are starting to move a little quicker. This is probably due to increased ocean heat in the region. Unfortunately, I don't know if I said this before, but East Antarctica is sort of known for lack of in situ measurements, so we don't really have a lot of measurements in the ocean there. We also don't know much about the seafloor bathymetry or bedrock topography below, so that is the main driver of how much water can get in and hit these glaciers. So better in situ data is needed for that. But this was all done using new ITS-Live data sets, which Alex is going to talk about now.
Okay, fantastic. So I'm just going to talk about a new NASA initiative. It's called the ITS-Live project. It's a measures-funded program, which is kind of creating these records, data records of changes in the environment. This is a collaboration between JPL, the University of Alaska Fairbanks, and the University of Colorado Boulder. So I just want to impart my enthusiasm for kind of the changes that are about to happen from the observational perspective. We have been very observationally constrained. We've had to extrapolate a lot of our knowledge from very sparse measurements of ice sheet change. But with the launch of several new satellites, that's kind of going to get upended. So, I kind of talk about this as a shift in paradigm for glacier research, because now we have a lot of observations that we're going to synthesize, and we're going to extract a lot of knowledge from them. So starting with the ESA mission, we had the launch of Sentinel-1 AB, so that's a synthetic aperture radar mission. The amount of data pouring in from that mission is very extensive. That gives us measurements of surface flow. In 2013, NASA launched Landsat 8, and later on the Europeans launched Sentinel-A and B. So these missions combined give us nearly continuous coverage of the Earth's surface. And so that's just taking images, but when we take those images and they have features in them, we can track those features through time and measure the surface flow. And then we had launch of NASA's GRACE follow-on mission in May. So this is going to be continuing the record of gravity changes or mass changes on Earth. And so that's measuring the transfer of mass from ocean to ice and ice to ocean. And then this September, we had the launch of IceSat-2. There's going to be a press conference on that tomorrow. And this is a revolutionary instrument that's counting individual photons that are being bounced off the surface. And so all of these new missions are bringing new data sets online and are starting to generate new insights into how ice sheets behave. And this is all driving the question of what is the future response of the ice sheets. And I should mention that in January of 2022, NASA's NISAR mission will launch. And this is going to be the first left-looking SAR mission, and so this is going to give us nearly continuous coverage around the pole hole. And so there's going to be sections of the ice sheet that we haven't been able to monitor before routinely. Okay, so now we'll just go into specifically the ITS-LIVE project, so the intermission time series of land ice velocity and elevation. Now, glaciologists have had a tendency to kind of have a niche craft of generating the data from kind of the low-level instrument data that's being collected by the instruments. And the whole point of ITS-LIVE is to try and remove that from the scientists' hands and just provide them the kind of end-level data that they can actually start doing the research on. So you can imagine the measurement itself is quite complex. There's a lot of corrections that have to go into it, a lot of data manipulation. You have all sorts of different sensors coming up, going down, different technologies. So how do we link that all together to create the best geophysical representation that we can through time? Once we have that, we can start linking it to changes in ocean, changes in atmosphere, start understanding what's going on. So these are all the missions that we can use to measure surface flow. And they have been around for a very long time, and yet the data sets to look at the change in flow over time are sparse or don't exist or they're not collated. So the ITS-LIVE project is going to reanalyze all of the data that's kind of boxed in red here. So we're going to go back, we're going to look at the Landsat 4, 5 missions, we're going to look at the Landsat 7, the Landsat 8, the Sentinel-2 data, Sentinel-1AB, and so we're talking about petabytes of data that we're developing a process chain for to synthesize all the data and give us continuous records of change. And so what does that look like? Well, this is just an example for Landsat 8. So if you take all of the Landsat 8 data, you have millions of pairs of images. And within those pairs of images, you can see subtle changes in the surface structure and basically the placement of the pixels within each picture. And you can track that. And you can create these records of flow. And you could imagine that the continent is often cloudy. And Landsat 8 cannot see through the cloud. But when you stack up so much data, you can start to kind of increase the signal, decrease the noise, and you can get these beautiful maps of flow. And so we can generate these annually just from Landsat 8, but we also have Sentinel-2 AB, and we'll also have the SAR Sentinel-1 mission to start creating these continuous records of change. For the Greenland ice sheet, we have a longer record because Landsat missions have been able to download the data. We were downlinked limited in the past, so the acquisitions were very targeted. So this is the flow all the way, showing the record back to 88. We can do this all the way to 1985. And this allows us to create a continuous record of change and start looking at what is it that's driving the increased loss from Greenland. And you can see that the coverage really increases after the launch of Landsat 8 in 2013. But even all the way back in the older missions, right around the coast, where you have a lot of crevasses and very well-defined texture in the image, we can track that texture in the image and create a continuous record of flow. Now, in addition to just looking at the flow of the ice sheet, we're also looking into the elevation change, right? So the elevation change is basically the integral of the mass change with some noise from changes in firn, but it tells us how much mass is being transferred from the ice sheet into the ocean. And we have a very long record of this because we've had ocean altimeters to measure the sea surface height. And so we take those instruments and we apply unique processing so we can understand what the changes in the ice sheet elevation are. And there's some complexities due to with how the radar signals scatter off the surface. The change in the instruments, we have laser altimeters and radar altimeters. But we can bring those all together, working with the low-level data to generate these very coherent maps of elevation change. And it's this much more robust processing that allows us to bring kind of the ice sheet into focus and kind of facilitate what Kathryn's doing. And so we can start seeing some of the more subtle changes that are going on and try and understand those in the context of external environmental change. And so you can see there's a clear drawdown signal in the West Antarctic. We all know about Pine Island and Thwaites glaciers there in bright red. But you can also see a distinct drawdown pattern for Totten and up along the east coast there. And that's what we talked about. That's what Kathryn covered in her presentation. And so we'll have some new discoveries coming from this. Now we also have, we're also going to be looking at the ice shelves. And so if we measure the height of the ice shelves and how that changes through time, that change in the ice shelf is happening through a number of things, but one thing that we can extract is how much the ocean is actually melting the bottom of these ice shelves. And that's very important because these ice shelves provide the back stress to hold the ice streams that flow into the ocean from flowing faster. And so we're very concerned about the ice shelves. We want to monitor them, see how much the ocean is influencing them, because if they thin, they weaken. If they weaken, the glaciers start to flow faster, and conversely. And this is an example just showing the very high detail that you can get out of these new data sets. And so on the left, you have a map of height, just raw height, and that's from a combination of all of those altimeters that I showed before. On the top right, you have the height change, and that height change is going to be converted into a melt, effective melt at the base of the glacier. And then just to highlight the detail that you get out of it, you can see the slopes that are coming from the altimeters. So this is really happening at a spatial and a temporal resolution that hasn't happened before. So the best we've been able to do is kind of extract decadal trends from these older observations, and now we're going to be able to convert that into something that's very high spatial resolution and temporal resolution so that we can start to understand the processes. So the data is very close to going live. We're going to have an initial release of a very small subset of the data in January, and then within the next year, we'll start getting that out into the hands of the researchers. And what we're hoping is that by putting the data in the hands of the researchers, they can get directly to the task of drawing geophysical understanding from the observations themselves. And so just in conclusion, I think we can anticipate that over the next 5 to 10 years, we're going to have a lot of observationally driven discoveries, such as what Kathryn's making, because of the new data that's coming online. And yeah, we'll take questions now if anybody has any. Thanks.
Is my mic on? There we go. Just remember to state your name and affiliation.
Seth Bornstein, AP. I guess this is for Kathryn. Can you go through some of the numbers again a little more slowly in terms of how much we are seeing in melt in those areas you were talking about in East Antarctica, and the speed of the melt, and how does this jibe with, for example, some of the Jay's Wally papers in the past, and a lot of papers that showed East Antarctica was not only stable, but might have been gaining mass. And finally, is this melt we're seeing, you're saying it's related to the ocean warming, is it natural variability or is it anthropogenic climate change?
Sure. Should be on. Gosh, oh, there it is. So to start with the speeds, so for the 4 glaciers that I was talking about in Vincennes Bay specifically, so since 2008, they've lost about 9 feet of elevation. So just, the surface lowered by about 9 feet. And that's about, over that time, it varied, but over that time it was about, I'm going to get it wrong, but 0.25 meters a year. I'm not going to do the feet correctly. 0.25 meters a year, lowering since 2008 till this year. The other thing that I was going to say, so that in case this sort of changes to velocities, but they also sped up in that time flow-wise, which I didn't cover, but they sped up about 3% of their 2008 velocity, which sounds small, but is significant enough to change the flux coming out of those glaciers because they're very deep. As for what was the second question? I don't remember.
So anthropogenic was in there.
Oh, yes. So for the natural variability part, so we certainly, I didn't talk about before 2008, we had elevation change records before that, thanks to the elevation change back 25 plus years that Alex was just talking about. And we could see that they were lowering before as well in the mid 90s or so, but then started ticking back up. And it actually is very correlated with ocean temperatures. But those were sort of unique events in the 90s, and now it's just a general trend that it's warming. So they are responsive to ocean temperatures, whether that's now it's becoming a trend that's it's increasing, not so much just one-off events that it's an influx of warm water. I don't know about the anthropogenic part. We didn't really look into that. We didn't look at the cause of the warm water.
Difference between this and swallowing.
Oh, yes. So studies like Jay's, Wally's, and some others that have suggested that, and sort of the background reasoning why we think, for a long time we've thought that East Antarctica is more stable than West, is sort of for the reasons that Alex was talking about with these new data sets that can look at these even smaller time scale, differences between, yearly or monthly rates instead of looking at an entire decade. You have a snapshot in 2005 and you have a snapshot in 2015, and if it doesn't look like it changed, you say it's stable. But in there, you probably had a lot of variability, you just couldn't see it.
All right, any more questions from reporters in the room?
Thanks. Robinson Meyer with The Atlantic. The Zwally question maybe got at this, but is this different than what we would expect from models? Is this something that we would, is this kind of melting captured by this kind of elevation loss captured by the sea level rise models, or is this more than we would expect? Thank you.
So I think one of the things to understand is that the Antarctic is still relatively undiscovered. So in order to be able to model what we observe, we would need to know what the bathymetry of the continental shelf is leading up. So we don't even know if warm water can get to the front of these things. So we're really limited in our ability to model kind of the forward projection of these things. I think one of the key things to take away from this study is what we're documenting is not a large change. What we're documenting is a consistent change that's forced at the front by the ocean in the East Antarctic. And so the reason we find this finding so impactful is that we're starting to see change that's related to the ocean. And believe it or not, this is the first time we're seeing it in this place. And so to forward model that would be incredibly challenging, and that's why observations like this are still kind of fundamental to our understanding.
Jonathan Amos from BBC. Question for Kathryn. Just because I didn't quite catch it, your explanation as to why now the ocean is able to attack these glaciers as they have been in the West. You suggested that something's changed there, and also for Alex, I mean, it's not just the amount of data that we've now got, it's the computers as well, isn't it? It's our ability to set the algorithms free, yeah?
So to just go first, the reason, so it's a hard thing to sort of back out why the ocean is warmer. We did that in a previous paper for West Antarctica, and this morning in my presentation, I talked a little bit about how we thought this was happening. And the reasons there that I gave were twofold. One is the winds are changing, or were correlated with the change in ocean temperature at that location. So if you get sort of a change in the winds, that change how the upwelling occurs on the continental shelf. So it can bring warm water up from depth. So that was one thing that we sort of could attribute this to. The other thing that that was highly correlated with the change in temperatures on the continental shelf, where we were, right out in front of the glaciers, was sea ice extent. So if you have more sea ice, this is our sort of hypothesis, is that if you have more sea ice there during the winter, then it sort of insulates the water below, and you get a warmer summer period after that. So we've seen an increase in sea ice over the winters in the past few years, in the past decade or so, in that location. So we sort of, the way we backed it out was it's both increased upwelling at that location from winds and increased sea ice cover.
The westerlies have increased there, have they?
So the zonal winds have decreased, so that means there's more easterly winds. So it's blowing, sort of making water move to the east instead of to the west.
Yes, thank you. Rich Blackstein, freelance journalist. I have two questions, one for each of you. First, for It's Live, is there an exact date in January where it'll go live? And for our editors' interest. And then for the East Antarctica, for this zone, is there anything in paleohistory that can inform our understanding, any precedent, and also any range of sea level rise in that paleohistory?
We were hoping to have the It's Live up by now, so we are working tirelessly to get it up soon. So let's just say late January is the best. Yeah, NASA has a lot of processes you have to go through to release stuff.
And as for the paleohistory, not a lot is known about that specific location, but what has been the single study sort of about the seafloor in that location was done in the 1950s. I can't remember the first author's name, but they took sort of a survey because it's near it's near an Australian Antarctic program base, so they could take a survey of the seafloor near their base. And they were attributing the big trough that sort of connects those glaciers to the continental shelf break. They were attributing that to a large iceberg scour. So there was used to be a glacier sitting there out to the continental shelf break, but that's just about all that exists.
Omer Irfan, reporter at Vox. The INBI mission reported this summer that there was a massive acceleration in the melt rate in Antarctica. I'm wondering if you can speak to the east versus the west ice sheet's contribution to that, to what extent that matters, and then what you can anticipate as average temperatures rise around the world and ocean temperatures rise.
Sorry, you referenced the INBI result in particular. So the latest INBI that came out, the acceleration for Pine Island and Thwaites is kind of leveled off from the earlier 90s and 2000s when it really started accelerating. Now, what was your specific follow-on from that?
To what extent does the distinction between the east and west melt rate to sea level rise, like to where that melting is sourced from? How does that matter and how does that play out?
Yeah, and that's a really good question. That's one that we're really trying to understand. And I think what it all has to do with is the access of the circumpolar deep water to the fronts of these glaciers. So the circumpolar deep water lies at depth, kind of below 400 meters depth. And when the glaciers have access to that, you can generate very high rates of melt. And that's what we've seen play out in the west. And so a lot of the response we're seeing for Pine Island and Thwaites and around there, and even in Kathryn's earlier work in the peninsula, is all driven by access of circumpolar water to the front of these glaciers. It's not the same as Greenland. So Greenland is very affected by surface melt. In the Antarctic, it's very much just driven by an ocean melt signal, but it's an ocean that's warm water at depth. And so the big question is there access of this warm circumpolar deep water to the front of these glaciers? We know for certain that water is getting to the West Antarctic glaciers. We are not as certain whether it's reaching these East Antarctic glaciers. And so it was only a few years ago that it was reported for Totten Glacier that the circumpolar deep water was reaching there. And it hasn't, I believe, been documented for any of the other glaciers. And so the work Kathryn's work is really highlighting that there's potential warm ocean water reaching these other glaciers as well. And so we're really just at the tip of our understanding of what the ocean influence might be in the East Antarctic. Anything you want to add there?
I guess just to note about why circumpolar deep water, especially in West Antarctica, is more effective is if I had a map. I won't go back, but so circumpolar deep water, like Alex was saying, is at depth, and it's carried by that Antarctic circumpolar current, and it runs right along the continental shelf break in the west, so it can sort of peel off warm water and dump it into the bays where these glaciers lay. East Antarctica, it's a lot, as it comes around the Antarctic continent, it's a lot farther removed from the shelf break, so it doesn't really have access to that continental shelf unless something changes in its flow.
Okay, I believe we have a question on the chat.
We have a question from David Appel, freelance. He says, do you know why Antarctic sea ice decreased so much a few years ago? And this is for both of you.
Yeah, speaking to the sea ice, I mean, I don't know. So there was a rapid expansion in the Antarctic sea ice, and just in the last few years, we've seen a sharp decline, and I'm not up to speed on the research. I don't know if you have anything to say.
Yeah, I'm not sure. I know a lot of people do. We aren't really sea ice scientists.
Yeah.
Fair enough. I have another question from Dan Bamberger, also freelance. We just had a record strong El Nino. How does that affect ice in Antarctica?
So we're not sure about East Antarctica yet, mostly because of the same reasons. Not much measurement and not much evidence of that circumpolar deep water. But nicely, we just had completed a paper a couple of years ago, or a year ago, that built on previous studies that showed circumpolar deep water, specifically in West Antarctica, in the Amundsen Sea, and along the peninsula, is really driven by the interaction between El Nino and the southern annular mode, which is basically the El Nino of the southern hemisphere. It's just another atmospheric pattern. So the sort of interplay between those two, we could see, strangely, in the Amundsen Sea, you see during a strong El Nino period, you get increased warming and increased melt of the glaciers. That was by Fernando Paulo, published that last year, I think. And then we showed that the same thing happened on the Antarctic Peninsula, but opposite. So when it was a strong La Nina event, you got increased warm water and melting. So there is a strong connection between global circulation patterns and, particularly on West Antarctica, ocean warming. But a lot more research to be done on that.
Thank you.
Do we have more questions from reporters in the room? Anything else on the chat? All right, that will conclude our press conference, and we'll reconvene at 2 o'clock. Thank you.